Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. We are working on chapter 7 where we discuss quantum systems in equilibrium. Let's quickly recap what we have done so far in this chapter. So quantum systems are of great interest, particularly from the perspective of quantum information processing, and also they are all of importance from the perspective of fundamental physics, because they offer the possibility of having phase transitions at zero temperature, which are called quantum phase transitions, and these by themselves are of tremendous interest for a variety of reasons. So motivated by these class of problems, we started looking at quantum systems in equilibrium, and we start off with a qubit, which is a zero-dimensional quantum model. We worked out the equilibrium state of the qubit and found that it is a fairly innocuous thing. Whereas when we looked at the one-dimensional transverse field Ising model, which is a higher dimensional system than a qubit in the sense that you have a bunch of qubits that are arranged in a chain, and these qubits interact with each other, we found that you can have variety of states there, some that break symmetry, some that don't. And working with these models, we were able to arrive at a rather intriguing and astonishing and even useful conclusion that a d-dimensional quantum system in equilibrium is equivalent to a d+1 dimensional classical system in equilibrium with possibly different coupling constants. This kind of an equivalence has been exploited quite a bit in physics, in variety of fields of physics, I must say, from condensed matter to high energy physics and so on. So what it allows us to do is it allows us to use classical descriptions or classical systems to study quantum systems in their ground state. So our goal is to study the ground states of certain quantum systems, and there is motivation for that is if we know ground states of certain quantum systems in d dimensions, we might even be able to say something about the d+1 dimensional classical problem. So we can also work backwards. So there are multiple motivations for studying ground states of quantum systems. So with that, in this lecture, we will start exploring the ground state of the transverse field Ising model as a function of the coupling constant. So let's briefly look at the transverse field Ising model in one dimension. So the way we set this problem up in the last lecture was to say that we have n sites with periodic boundary conditions. So the nth site is identified with the 0 site, and at each site we have a two-dimensional Hilbert space of a qubit. So a qubit resides at each of these sites. The basis states are chosen to be the eigenstates of the Z operator, the Pauli Z operator at the qubit site. And the overall Hilbert space of our model is the tensor product Hilbert space of all these qubits. So since it's a tensor product, the basis states of each qubit, if you tensor product the basis states, you can get the basis states of this V, which is the Hilbert space of our system. And you can see that dimension of V is 2 to the n. Okay, we can put down a Hamiltonian which involves two pieces. The first one is an Ising interaction. So it just looks at the Z operator at a site I and it multiplies the Z operator on the next site. So what it wants to encourage is it wants to encourage the qubits to have their degrees of freedom pointing in the eigenstates of Z, and they have to be parallel on neighboring sites. So that's because this is J is chosen to be positive. And then we have a transverse field, and we have a global Z2 symmetry generated by this flip operator. Now, using the symmetry breaking field trick, we can find that the ground state when H is equal to 0 and J is positive is the all up polarized state, right? So this is this double up arrow. and the Z2 symmetry is broken, and the order parameter, the magnetization per site, is unity. If I look at the other limit where J is equal to 0 and H is positive, then the state has all right polarized or all X plus polarized. So it's the eigenstates of X with plus 1 eigenvalue, and that is what we mean by this. And here the magnetization is 0. And this does not break the Z2 symmetry. So what is the question we would like to ask? So the natural question is, if I look at these two limits, I am able to solve the problem, but what is the ground state at some arbitrary value of H by J? What I mean by that is both H and J are non-zero, and in particular, is there a phase transition in going from the magnetized state with m equal to 1 to the 0 magnetized state, as I say, for example, increase H keeping J fixed, let's say. So if you think about this, you will see that there are three possibilities. The first one is you have broken symmetry for every value of this parameter H by J. So you start with H by J equal to 0 where m equal to 1, and it sort of smoothly comes down, and for any value of H by J it is finite and positive. Positive because of the choice of our direction of symmetry breaking field. You could have other possibilities. So for example, the magnetization could sustain until some point to a finite value and suddenly gives way, abruptly jumps to 0, and then it is 0 after certain critical HF. HF could be some value of H at which there is a first order transition. The third possibility, which is perhaps the most interesting possibility, is that there is a continuous phase transition. What do we mean by that? So the magnetization starts at 1, it is continuous, so there is no discontinuity in the magnetization. It comes down to 0 at a critical value of the field, which is called HC, and then it remains 0 for larger values of H. So these are the three possibilities. We can sort of, this is sort of common sense. I mean, you just look at this and these are the obvious things that come to your mind. So what would be your guess? Maybe you should pause the video and think about which one of them could be the correct answer. Okay, I'm sure you have guessed, and therefore we should now confirm that guess by a calculation. Okay, how do we find the ground state of such a Hamiltonian? So the problem is obvious. We had a problem when we did the classical problem. When we come to the quantum problem, the problem is manifold difficult. And if you think about the dimension of the Hilbert space, for just 20 sites, this will be a million by million matrix, right? That would be the size of the matrix that you will have to diagonalize. If you set up the Hamiltonian matrix in the 2 to the n size, then it will turn out to be more than a million by a million. And it's practically impossible to obtain the full spectrum. And if you really want to look at some thermodynamic quantities, etc., then n must be large, and then you're lost right there. If you are interested in the ground state, I must mention that there are very nice and very powerful methods called as density matrix normalization group, and there are modern variants of this using matrix products, states, etc. And in fact, I must even mention that there are even neural quantum states which are sort of inspired by machine learning and all that. So there is a specialized effort in trying to get to ground states of such Hamiltonians. So this is good to be aware of. So we are going to be much more modest in our approach. We are going to use perturbation theory, just elementary perturbation theory, which we have studied in our first year quantum mechanics courses. And this is the analog of the series expansion that we did in our studies of classical systems. So how do we do perturbation theory is the following. We always try to find a state for which we know the exact ground state. So in particular, when H is equal to 0, we have the ferromagnetic state, and we can start with the ferromagnetic state and do perturbation theory about the ferromagnetic state. On the other hand, if h by j is much greater than 1, then I could choose the h greater than 0, the right polarized state, and use j by h as a small parameter, and I can do perturbation theory in that. Okay, so let's start by looking around the ferromagnetic state. So I'm going to keep the transverse field to be 0, and I'm going to first find the spectrum of the system at h is equal to 0. So once I know the spectrum at h is equal to 0, I can look at the states in the spectrum and ask how they will evolve when I turn on a finite h. So you can probably guess what is the spectrum when h is equal to 0, because the problem is essentially classical. There are no non-commuting operators, and so this problem is essentially the classical Ising model in one dimension. So the ground state is the fully polarized state, and the way we constructed this is using the symmetry breaking field ansatz. And the first excited states we know are domain wall kind of states. So what we have here are two links that have gone higher energy because the two spins that are in touch with that link are opposite in direction. So you'll get a domain wall here and a domain wall here, and all these spins here have been flipped to the down state. So how do I label such a state? This state is conventionally labeled by starting with some site I1 and ending with site I2, and we will use the convention that I2 is greater than or equal to I1. Okay. So this state has an energy 4j above the ground state. So why do I have 4j above the ground state is also fairly obvious, because this link will cost me 2j of energy because it has gone from minus j to plus j, and this link will cost me another 2j of energy, then that gives me the 4j in total. Okay, so this manifold of states have an energy of 4j. You can see that these states are also, there is a large degeneracy. The number of spins that I need to flip to reach a state like this, you can just count I2 minus I1 plus 1. That is the number of spins I have to flip to reach this. Okay, so this is the 4J manifold. Manifold, by manifold I mean the set of all states. You can think of the subspace of the Hilbert space, which has which is at a state an energy 4J above the ground state. So that subspace is also called a manifold, the manifold of states. So we can call it the 4J manifold. So the second excited states are those with 4 domain walls. So you could label them in the following way. You could label the first domain wall by I1, I2, and the second domain wall by J1, J2, and so on. And you can collect all these domains in this fashion, and you can label them like this. And you use some nice convention to so that your bookkeeping is clean and nice. And it's not difficult to see that this state will be Hj above the ground state. Okay. So now comes the question, what is the ground state when H much less than J? So to find the ground state, I have to find some perturbative expansion of the ground state. And how do we do this perturbation theory? So let me walk you through this carefully. So you will realize that in performing this perturbative calculation, states with single spin flip are very important. So what do I mean by a single spin flip? So this is the smallest domain of downspins possible. And so we can label this as a state located at site I with the spin down there. That's the convention. And this is same as the finite domain case where I1 and I2 are equal to I. And you can just use a counting formula and you will find that the number of flip spins is 1. So why is this particular manifold of a single spin flip very important in our discussion? So the important thing to remember is that when H transverse field acts as a perturbation on the fully polarized state, it will produce a state which is in this manifold of single spin flip states. It will produce, when HH acts on the fully polarized state, it will produce a linear combination of states where those linear combinations involve states with spins flipped at different positions. If you take one of the operators that make up HH, namely this X operator at a site I, and if you act that on the fully polarized state, you will see that it will actually produce this state with single spin flip at site I. That's fairly straightforward to see. Okay, so in the 4J energy manifold, we have a sub-manifold or a subspace of those states with single spin flips which we claim are important. Why are they important? Why are for example one spin flipped here and another spin flipped here, so that there are two spins flipped? Why are they not important? So the idea why they are not important is, if you want to include those states in the perturbation theory, they have to come at higher powers of this transverse field, because to start from a ground state and to reach a state where I have flipped two spins, I have to operate HH, this transverse field operator, at least twice. So this will not contribute to the lowest order in perturbation theory. So our again goal is modest. We want to compute things to lowest order in perturbation theory. So a good place to start would be to just focus on these states where I have a single spin flip and extract some physics out of them. We can improve our calculations with more detailed analysis of two spin flip, etc., but we can start with this. Okay, so this is the setup, and so we can ask, how do I get the ground state energy when H is non-zero by using perturbation theory? Okay, so I'm just going to use the perturbation theory formula, which is actually a very well-known formula which all of you have studied in elementary quantum mechanics courses. So I have the ground state energy, which is now indicated here as a function of H to inform us that we are going to find the ground state energy at non-zero H. That is equal to the ground state energy at 0 H. This is just minus n times J, J being the exchange constant. And then I have to take, if you recall your perturbation theory, the first order term will be simply the expectation value of the perturbation operator on my original ground state. But you can see that this matrix element, this expectation value if you wish, will be 0. Why is that? Because HH, when it hits on this fully polarized up state, will produce a linear combination of downspin states where a spin is flipped at a single site. Those states are actually orthogonal to the fully polarized state. And because of that, you will see that you will get a term here which vanishes. So there is no linear order correction in little h, the transverse field, in the ground state energy. Okay, so this is the first observation. Okay, what is the second term here? The second term is a second order effects. So what do I have to do? I have to see, I know that this HH to linear order will take me to the manifold of single spin flips. So I simply look at the space of those states, and they are spanned by this I down states where I can be any of the sites. And I just find the matrix element of this transverse field operator hitting on my ground state, and what is the overlap of that that state that I get with my I down state, and I sum over all i's. So I sum over the complete set of states in that manifold. And what is this minus 4j? So if you just recall your analysis, so that will be the energy of the ground state minus the energy of the excited state. So you will end up getting this term, which is minus 4j. Okay, so what is this matrix element? Now that is very easy to see, because you know that I down state that is shown here is X operating on the fully polarized state, and HH has a minus H hitting Xi here. So this matrix element is simply minus H square, okay, minus H the whole square. So you'll end up getting that this answer of this term here is H square by minus 4j. And how many such contributions will be there? One from each site, spin flipped at each site, those states, and so there are n of them. So this term will turn out to be proportional to n. Now what I can do is I know ground state energy is minus n times j. So I can take the n out common, and I will end up getting minus nj times 1 plus 1 by 4 h by j square. Now remember, this is a small parameter. And so we have now pulled off the ground state energy as a function of h by j. And the nice thing to note is that this is correctly extensive. So ground state energy is proportional to number of sites, which is a nice result. You should always check this. So we can be pretty happy about this. So that's the ground state energy at an h which is non-zero, but small compared to j. Of course, you can go to higher orders, etc., and do calculations. So if you are interested, you should try those things out. Okay, let's now produce a result for the order parameter. So we have found the ground state energy, and we would like to know what is the order parameter. How does that evolve as a function of h, little h, the transverse field? Okay, so for this I need to know what is the ground state at a finite h, and I can go through the very same perturbative calculation. So let me walk you through it. So I'm looking at the ground state at small h. So that again by perturbation theory will be my ground state when little h is equal to 0, plus I look at the amplitude, the matrix element of the ground state with the single spin flip state, and remember that is minus h, and I just linearly combine all of these, sum over all sites, and that will be my ground state. Now based on the discussion from the previous slide, we know this is minus h, so this quantity just becomes h by 4j, and this is sum over I, the set of all single spin flip states. Okay. Now we would like to compute the expectation value of the magnetization. So the expectation value of magnetization m, which is our order parameter, is the expectation value of this operator m, which is like the average value of the Zi operator on each site. So remember that this ground state is not normalized. So to do this calculation, I have to be a little careful in making sure that I make the correct normalization. So it's the matrix element of this magnetization operator in the ground state, expectation value of that, divided by the norm of the ground state. So if you go through this calculation, it's not very difficult to see the calculation. I'll just walk you through it quickly, give you an argument as to why this result is true for the numerator. So when I hit m on this, just keep the 1 by n aside. I've kept the 1 by n aside here. If I sum over Zi and hit it on the fully polarized upstate, my answer will be n times the same state, upstate, because each site will contribute +1 for me. If I hit this m on the state I down, which is the single spin flip state located at I, n minus 1 of the states will contribute plus 1, and this state will contribute minus 1, which means the eigenvalue corresponding to this state, which is an eigenstate of the m operator, is n minus 2. Now you simply observe this and take inner products and take the dot product with the state itself, and then you will end up getting this nice result. So it is n plus n times n minus 2 times h square by 16 j square. This comes from the fact that this will, when you inner product it from the other side, you will get this factor of square of h by j. Okay. Now it's not very difficult to do the inner product of the norm of the state itself, and that will turn out to be this. First observation is, in the numerator there is an n and there is a 1 over n, so they will cancel. So I'll get it to, the numerator will turn out to be what I have here. And then I have a denominator which is 1 plus this quantity, and I'm going to assume that this h by j square is really small, and then I'm going to expand this in this fashion. So that's the approximation. And you see something very nice again. This magnetization should not have any factors of n, because if the magnetization has a factor of n, the answer is somewhat maybe suspicious, right? So you see some link cluster theorem kind of thing going on here. So the power of n in the denominator actually cancels some powers of n in the numerator, and you get a correctly extensive result, right? And you get that the magnetization is 1 minus 1 by 8 h by j whole square. So this is a very nice result now. What is so exciting about this? So our calculation is now showing us that the broken symmetry state at h is equal to 0 survives when I turn on an h, and if I keep it really small, I can control the calculation and I can find that the magnetization reduces, but only very slightly, right? So for example, if h by j is a tenth, then this will be 1 by 100 and it will be 1 minus 1 by 800, right, which is really a small number. So that's a very nice result. We find that the broken symmetry state survives at a finite h. So what have I demonstrated to you? We have a broken symmetry phase. That means there is a regime of parameters in which the same state sort of appears. This broken symmetry state appears. So that's what we typically call a phase. Okay, so this is very nice result. We should be happy that we have reached this point. So it says that the magnetization starts at 1 when h is equal to 0 and comes down. But unfortunately, the three possibilities of crossover, first order transition, second order transition, or continuous transition, that cannot be settled by this calculation. All of them we expect to come down when h starts off at 0. That's what we at least guessed. Okay, so we have solved the problem, but not quite, we haven't got to the solution that will give us insights into the question we asked. We may have to come back to this later. For now, let's continue our discussion of this problem itself. So remember, I had a manifold of excited states of single spin flips, etc. And then I had these manifolds of excited states where there are multiple spin flips and domains and all of that stuff. What's the story with those guys? You see, they were gapped. They were 4j above ground state. So the question to ask is, does the gap survive? Do they become very close in energy with the ground state, or still you have to pump in some energy to go to those states? So we have to study the excited states. Okay. So the excitation gap at h is equal to 0 is 4j, and the question we are asking is, how does this change when h becomes greater than 0? So the first thing one has to observe here is this transverse field term h little h can admix states in the first excited manifold without changing their energies. What I mean by that is, degenerate states in that manifolds can be mixed by HH. For example, when I did the ground state calculation, When HH hit the ground state, it was not in the ground state, it took you out of the ground state manifold and you went to the first excited state manifold. The statement I am making is, if you take the H is equal to 0 problem and look at the states in the first excited manifold, there is a linear perturbation term in H that can act on those, in the sense that they will admix all the degenerate states in the first excited manifold. How do we see the physics of this mixing? I have to tell you that the calculation I am going to show here is somewhat rough. It is not a precise calculation. The precise calculation may be interesting to do and also, little lengthy. So we will take an approach where we are physically correct and yet we see the physics nicely. So to see the physics, what I am going to do is, in the first excited manifold, I am going to isolate a set of states which I call as DI. So you can sort of, it's an acronym for domain until site I. Okay. So here in these class of states, the leftmost flipped spin is at 0. So at the origin, the spin is flipped, origin of your 1D lattice. Okay. So the periodic boundary condition, that link has got to excited state. So we'll just fix that link there. And then I'm going to construct states where all the spins up to the site I down are also up to the site I are flipped to down state. So this will of course require I spin flips. Let's say that has been done and you get this state. Okay. Now ask yourself, what does the transverse field operator do to such a state? Now remember, the transverse field operator has one of these operators sitting inside. So that is xi plus 1. So that corresponds to taking this spin here, and if the xi plus 1 operator acts on this spin, it will flip that spin. So how do you interpret this? This can be interpreted as the domain wall. Remember this, the domain wall, the red thing, hopping, quantum mechanically hopping from this site, which I am showing in some purple color, to the neighboring site. Now what site is that? That's the site of the dual lattice. So you can now physically see that if I look at the manifold of states spanned by these DI states, the transverse field operator will produce some kind of a hopping matrix as the effective Hamiltonian between these states. So here I have put down the result that I just said in English. The matrix element of dj with the full Hamiltonian, that includes both the Ising term as well as the transverse field term, is 4j times delta ij. What is the meaning of this? 4j comes from the fact that in any one of these states, you will have two links in the excited state, so the energy is 4j. Remember, this 4j is split between the 2j energy in this link with the last link, which we are sort of keeping fixed in this discussion, and this link which is being hopped by this x plus operator, this x operator. Okay, and then I get this term. What does it tell me? It tells me that if xi plus 1 acts on this state, it will hop it this side. If xi acts on this state, I will hop it to back. I will hop it one back. No? So for example, if I hit xi on this spin will be flipped back. So it's as if the domain wall has moved one left. So that is how you end up with this matrix element. Now, if you recall from your elementary condensed matter courses, this would be the matrix element of a tight binding model of particles hopping on a chain. So if I diagonalize that, and remember that this 4j energy is split between one of these fixed link in our discussion, a fixed excited link, and the link that is moving along, then you will be able to see that the dispersion of this hopping domain wall, it's like a particle, goes as 2J, with 2J is the energy of this single excited link, minus 2H cos K, where K is the crystal momentum in the Brillouin zone of this dual lattice. So if A is the lattice spacing of my lattice, the dual lattice will also have A as the lattice spacing, which is the distance between this purple squares. K will lie between minus pi by A, the first Brillouin zone of this kind of lattice, minus pi by A to plus pi by A. Okay. So what do you learn from here? First is that the excited state energy, which was 2J for a single, if you wanted to excite a single link from minus J to plus J, has now reduced. It will reduce depending on the crystal momentum. So for example, if I choose the crystal momentum to be 0, then I will see that the energy of the state will become 2J minus 2H. So the energy of excitation has been linearly reduced. Okay, but interestingly, you will see that the gap will not close for small h, because when h is much smaller than j, this number will still be positive. So your excitation gap will be finite. So what have we learned from this? We have learned that the system will continue to be gapped, but quantum fluctuations, what do we mean by quantum fluctuations? The transverse field operator produces excitations because the fully polarized state is not an eigenstate of the transverse field operator. It is not an eigenstate of the transverse field operator because the transverse field operator does not commute with the Ising term, the ZZ term. Therefore, they cannot have simultaneous eigenstates. This produces what we call quantum fluctuations. So quantum fluctuations are these excitations of single spin, flip and back. Those quantum fluctuations will be produced and they will reduce magnetization. So for example, this ground state becomes this admixture of the fully polarized state, quantum coherent admixture of the fully polarized state and this state of single spin flips. And you can see that this state where I have this I down is something like this coherently mixed state of where the single spin flip is all over the, it sort of runs all over the lattice. So this is the idea, and this is what we have discovered. Okay, very good. So this is a nice calculation and it tells us something interesting. But I have to give you a different perspective on this. Now, think of a universe which is made out of qubits at the smallest scale, some scale, we don't know, some micro scale, and they are arranged along a chain. So the universe is just, let's say, one dimensional and there are these qubits there. Suppose the Hamiltonian of this qubit were a transverse field Ising model which h greater than 0 but h much less than j. So sorry, there should be a script j, we'll fix that. So creature living in this world will see that the fully polarized state plus this linear combinations etc. as the vacuum, but they will observe massive particles. Now what do we mean by massive? So you know from relativity theory that if I want to create a particle of mass m, I have to have an energy of mc square. So that's like the rest mass energy. It's the energy required to create this particle. So this 2J energy is exactly analogous to that. So you can imagine that's the amount of energy I need to create this particle. So I go to the excited state manifold and then it will hop around and it will reduce its energy a little bit by gaining kinetic energy, right? And this is a dispersing particle, which means it has an E of k. So it is, it has an energy which depends on momentum. Okay. Now I'll give you even more astonishing result here. These particles are actually their own antiparticles. How do we see this? So think about the action of Xi. Remember, Xi hops states, right? So you can imagine that this Xi, if it is there, it will hop the domain wall on the left side to the right side. So now if I take the state I down, there is a single spin flip here. If I hit xi on it, I can interpret this as being flipping the spin back, or I could imagine that I am hopping this domain wall into the other domain wall, and when they meet, they annihilate each other, and that is the statement by which, that's the statement I'm making, that they are their own antiparticles. So these domain wall excitations now become some kind of particles that hop in this world. And so you can see that this broken symmetry phase of transverse field Ising model is some toy universe. So this universe has some vacuum where there are no particles, and then you can excite particles which are their own antiparticles, and they disperse in this universe. So it's a small, very humble universe where there's just this one kind of particle. Okay. So it's a good time to summarize this lecture. So the main points I've discussed today are, our goal in this lecture was to study the ground state of the transverse field Ising model. So this system has a broken symmetry state when the exchange coupling is positive and the transverse field is 0, and a symmetric phase when exchange coupling is 0 and the transverse field is positive. And our question was, how does the system evolve from this one limit to the other limit? We performed perturbative calculations around the ferromagnetic state with H is equal to 0, and we learnt a few things. So we learned that the broken symmetry phase survives when H by J is much smaller than 1. And most interestingly, we learned that quantum fluctuations make these domain wall excitations into mobile particles with a dispersion. Okay, and they gain kinetic energy in the sense that they delocalize, just like an electron wants to delocalize on a lattice. And this is the physics of what happens at small values of H. Okay, it's very natural to ask what happens in the other limit when the exchange constant is much smaller than H. So what I will do in the next lecture is, I will start with the problem when little h is a finite number and j equal to 0. I will list out all the states and excitations there, and we will do a perturbative calculation and ask the question, is there a different universe there as well? So I'm sure you will be very curious to know that, and I look forward to seeing you in the next lecture. Thank you.